Hey, Daniel.
Oh, hey, Gio. How's it going, man?
Not much. What are you up to?
I'm just, getting ready for Whoa! Did you hear that? What was that?
Do you think what I think it is?
I'm not sure, man. Maybe we should go check it out.
Yeah. Dang, just what I thought. That's another one.
Such a shame. Yeah. That bird can't be happy.
Yeah, that's definitely an angry bird.
Another one bites the dust. Another one bites the dust. And another one gone, and another one gone. Another one bites the dust. Hey, hey, we're gonna get you too. Another one bites the dust.
Gio.
And I'm Daniel.
And we've been working on a project called Angry Birds.
And in this project, we've teamed up with some researchers from Pennsylvania and Minnesota who are working on a solution to stop the problem of birds colliding with windows. Our goal this quarter was to design a system that would reliably test the effectiveness of their solution. Collisions with windows is believed to be the leading cause of bird deaths in the United States, with estimates ranging from 100 million to nearly 1 billion bird deaths annually. In the figure on the screen, we have the deaths in millions on the x-axis and the cause on the y-axis. It's easy to see that windows are even more deadly to birds than their predators, the cats. Birds play an important role in our ecosystem. Some eat lots of insects and rodents, which keeps their population in check. Others assist in pollination, while some assist in reforestation by ingesting seeds. Some people just enjoy watching birds as a pastime, so there are many reasons why we should care about the well-being of birds. The reason birds run into windows is the reflections of nature that they see in the window. They think they see another tree or bush in the distance and try to fly to it, which of course does not go as planned. For these reasons, the researchers we've teamed up with are developing films that have an ultraviolet reflective pattern on them. Using a part of the UV spectrum is advantageous because humans cannot see UV light, but birds can. By placing these films on windows, the hope is that birds will be greatly deterred from flying into the window, with minimal reduction in the quality with which humans can see through the windows.
The Angry Birds project is an ongoing project in the Engineers for Exploration group in which we designed and built an embedded system that will record data when a window collision is detected. We use sensors to detect vibrations and a web camera to verify the source was a bird. These systems will be used to measure the effectiveness of the UV films that the researchers are developing. The Angry Birds embedded system consists of a Beagle Black, two ADXL 345 accelerometers, a web camera, and a status blinking LED. The Beagle Black is placed in a metal enclosure for protection purposes against the environment.
The ADXL 345 is a digital accelerometer we use for our vibration sensor. It communicates with the Beagle Black using the I2C protocol. The Beagle Black is effectively a low-cost computer on which we run Ubuntu Linux. It handles all of the processing we need, as well as communication with the other peripherals in the system.
The web camera is a Logitech C920 HD Pro capable of 15 megapixels and equipped with Carl Zeiss lens. The camera is connected to the board via USB, and the system will not operate unless the camera is connected. The webcam takes 20 picters every second and stores it into a queue-like data structure, and the system pops off the oldest pictures when the capacity is reached. The LED is a standard 5mm LED that is connected to the Beagle Black GPIO pin that controls the blinking rate of the LED during certain conditions. Under normal conditions, the LED will blink at 1 blink per second, and under collision detection, about 5 blinks per second. The LED also serves as a system indicator informing the user the status of the system. As you can see, the Linux terminal is open, which we can look at debugging output of our program. When deployed, the program will automatically be started when the system is powered on. So to get the data from the system, all that needs to be done is to unplug the system and remove the microSD card and use the SD card adapter that comes with it to plug into the laptop. On the right, we have data from one of our tests with the system. The data is in the form of a video, which is the result of converting the images saved from a detected collision into a video file for ease of viewing. As we play the video, you can see an empty roll of tape colliding with the window on the left, and a line is printed on the terminal stating that sensor 1 detected the collision. Then, we throw the same object at the window on the right and see a line printed on the terminal stating that sensor 2 detected the collision. This shows that how we can monitor two windows using only one camera, since both sensors work independently and we only need one to trigger to get visual data for both windows. Thank you for watching our video, and a big thanks to Professor Kastner, who already set up funding from the zoo.
Plans are to take 18 of these bad boys up to Minnesota in about a week, in which we'll be doing real testing on windows that have these experimental UV films. We think our systems will have a large impact on finding the best solution to reducing bird deaths due to window collisions. And remember everyone, bird lives matter. I think that was pretty good.